Hello, my name is Robert Morgan. Welcome to my video on using Fourier model graphic organizers in mathematics to solve word problems and help create language. Fourier model graphic organizers are extremely useful for organizing ideas. They help students to create their own language or concepts in their own words, and they can help students build an example space of examples, non-examples, and extreme examples. The Fourier model has four parts. The first part, in the center of the page, is where you state the word or problem you would like to solve or define. The second part is the definition that the student puts in their own words. The third part is facts or characteristics of a word. This can be something as simple as, in an intercept, it's the point where you cross an axis. The third part is examples. Here you can define useful examples for students to view later and help build their example space. And no example space would be complete without the non-examples as well. Set up a couple of examples here using a Fourier model graphic organizer. The first example is with sine law. I've defined sine law in the middle as the word I would like to do. For the definition, in my own words, I've said sine law states that the ratios between angles and their opposite sides in a triangle are equal. For facts and characteristics, I wrote down what that means in terms of a math equation and drew a picture as well. For an example, I picked a triangle with sides 6 and B and opposite angles 30 degrees and 90 degrees. So using this, I can find that B is equal to 12. I can verify this with a ruler and drawing the triangle to scale. For my non-example, I used a square, and I showed that 2 and 4 do not work if I attempt to use the sine law. They don't have opposite angles, and if they did, sine 90 degrees is always 1. For my second example, I chose to use y-intercepts. I defined the y-intercept as the point where the graph crosses the line axis. For facts and characteristics, I defined it as simply the letter b in the equation, y equals mx plus b. For my examples, I gave a generic linear graph and noted the point where it crosses the y-axis. For my non-example, I gave another generic linear graph, this time negative, and noted the point where it crosses the x-axis. Word problems can be some of the most difficult problems for students to solve at the secondary level, but do not fret, we can use Fourier model graphic organizers to help. The Fourier model graphic organizer for word problems is just a little bit different. Rather than what we did before, this time we have the problem in the center, facts in the top left corner, unknown in the top right corner, setting up the equations in the bottom left corner, and solving in the bottom right corner. In the middle, you'll just put the problem, perhaps the whole thing, but most likely the number of the question you're about to solve. In the facts area, you're going to list all the information given to you, perhaps assist numbers, or other useful tidbits. In the unknown, we're going to set up what we need to solve and assign it a variable. Setting up the equations, we'll call on our past knowledge and our example space of definitions we had defined before to set up how we're going to solve this problem. And finally, with the solve step, we'll carry out all the operations necessary to come to an answer. For my example, I've chosen to do a simple distance equals velocity time problem. John walks 3/5 of a mile every 15 minutes. If John walks for 3.5 hours at the same rate, how much distance will he cover? For the word problem, I've listed all the information given. Our speed is equal to 0.6 miles every 15 minutes, or 2.4 miles per hour. For the unknown, I realized we had to solve for distance after 3.5 hours, and I assigned the variable d to represent distance. Drawing from a previous knowledge, I've set up the equation distance equals speed times time, or velocity if you want your students to use it that way. And to solve the problem, I put all the numbers into the equation, pulled out my calculator, and solved that after 3.5 hours, John will have walked 8.4 miles.